Okay, so this is a problem about rolling, particularly rolling downhill. So these kinds of problems are the types of problems that are constrained, meaning that translation and rotation are related. In particular, rolling is translation plus rotation. So translation is things moving this way, say, and rotation means them moving this way around a center. When you add those together, you get rolling, where the top moves more than the bottom, and the bottom is instantaneously at rest. So this was a problem where we said you have something of height h and an object rolling down a hill. Okay, the constraint means that the velocity of translation, v, is also equal to the velocity at the edge of the rim. Not any velocity, the velocity at the rim. So it's omega times of the rotation times r at the rim. Okay. Okay, so we use the work energy theorem, which says that the work that's done is the change in the kinetic energy. The work that's done is the work done by gravity here. It's the only force acting. Well, that's not strictly true. There's also a normal force, but the normal force acts through the point of rotation. So that normal force doesn't exert any torque around the center. So the work done by gravity is the change in the kinetic energy. We have the kinetic energy of translating plus the kinetic energy of rotating. So mgh is equal to 1/2 mv final squared, that's translation, plus 1/2 I omega squared. And we realize that these are related. So in fact, we can, instead of omega, put v divided by r. So we'll simplify this, 1/2 mv squared plus 1/2, and I is some number times mr squared. And then omega is v over r. So this number, the biggest it can be is 1 if you have a hoop. And for things that have mass distributed near the middle, it's going to be less than 1, say for a disk or a sphere, something like that. Okay, so we're left with 1/2. And now here's something interesting, right? The m's actually cancel. The mass doesn't really matter here. And so we have GH is 1/2 1 plus, so here's the 1 here, plus the box, and whoops, this was squared. So this r squared and this r squared cancel, and we have v squared as a constant factor. So we can solve this for v, and we get that v is 2gh 1 plus whatever that number is out in front of the moment of inertia, and take the square root. So the object with the smallest value for box wins. It has the highest speed. So the point mass has a box of 0. It doesn't have any moment of inertia, so it wins. And the hoop, which has the box equaling 1, is the last to finish. Okay, there you go. That's it.